Hello everyone. Today in this video we will be covering the chapter of carboxylic acids. Now remaining we have the reduction of carboxylic acids left first to discuss. Now we know that primary alcohols oxidize themselves to carboxylic acids eventually after first oxidizing themselves to aldehydes by heating under reflux along with acidified potassium dichromate. Now that means that carboxylic acids can first of all be reduced to primary alcohols. Now the reagent used is lithium aluminium hydride. The formula is LiAlH4 along with the condition of anhydrous ether. You don't need to know the chemistry of ethers for your AS syllabus, you only need to know the name. It is in A2. So first you need to know that you can have any carboxylic acid and that would be reduced to a primary alcohol. Now the carbon chain, the length of the carbon chain must remain the same. You can see that we have a 2 carbon carboxylic acid and that gives a 2 carbon alcohol. Now the second reduction equation that we can use is kind of the same. It's a random carboxylic acid, a 5 carbon carboxylic acid, and it reduces with the same conditions to a primary alcohol, a 5 carbon primary alcohol. So again, this is what you need to know for reduction of carboxylic acids. Now the next reaction that we will be doing is acid hydrolysis of esters. Hydrolysis of esters was a name mentioned that we came along in an earlier video. Over here is the detail of that hydrolysis. Hydrolysis occurs when the ester linkage, the C double bond O single bond O, is broken and the water molecule adds across the ester linkage. Now we will be looking into how that is theoretically implicated in these reactions. First we'll be studying acid hydrolysis and then we'll be studying alkaline hydrolysis. Now in acid hydrolysis we can clearly see that the reagents are dilute acid, so it must be acidified and it must have heat under reflux because there is to be a C single bond O broken, right? So this is the ester, any ester. Over here we can see that we have a 3 carbon ester. We know this is the acid part and we know this is the alcohol part. Now what happens is in the ester linkage in acid hydrolysis, the C single bond O is broken and a water molecule is added across this ester linkage. So the C double bond O gets an OH and the CH3O of the alcohol part gets an H. So you can see that this got the OH and this got the H. So this is basically acid hydrolysis. Another example you have over here, the ester linkage is broken, it receives an OH and this O will receive an H. So this is as simple as it is. This is acid hydrolysis. Now alkaline hydrolysis, however, is a little bit more complicated than this. Now in alkaline hydrolysis, the reagent is sodium hydroxide. It must be an alkali, aqueous, and heat, not heat under reflux. Now one thing to note is that in this also the ester linkage will be broken, but something different occurs, and now we'll be looking at the products first to tell exactly what occurs. Now if you look at the products, you are not getting a carboxylic acid and an alcohol per se as you were in acid hydrolysis. Rather, you're getting a salt and an alcohol. Now what exactly occurs in this? Let us look at the mechanism in a very simplistic way. The ester breaks into a carboxylic acid and an alcohol as previously discussed. Why does this happen? Because the ester linkage is broken. So if the ester linkage is broken, this will form a carboxylic acid by adding the OH to C double bond O as we previously discussed, and this will form an alcohol by adding an H to the O. But exactly what happens is that the reagent is NaOH. That means the sodium is present, and we know that acids react with alkalis, right? So when an acid, a carboxylic acid, will react with an alkali, what does it give exactly? It gives salt. It gives a salt. But an alcohol cannot react with an alkali. We already discussed this. So what do we get in the end? We will get an alcohol and a salt. And why are we getting a salt? We are getting a salt because the acid, the carboxylic acid, is formed, but it further goes and reacts with the alkali and it forms a salt. So that is why we are getting a salt and alkali and alcohols, right? So alkaline hydrolysis of esters will form a carboxylic acid and an alcohol, but the acid goes ahead and reacts further on with the NaOH, and it reacts to form a salt, and we have alcohol as a byproduct also. So in the equation you will see that there is a salt and there is an alcohol, and that is all that you need to know about alkaline hydrolysis. Now the last thing to discuss in this chapter is the commercial importance of alkaline hydrolysis. Now alkaline hydrolysis is used in a process, in an industrial process known as saponification. Saponification is also known as the formation of soap. Yes, this is the same soap that we use in our daily lives. Now, soaps are partly fats, and fats are glyceryl triesters. You don't need to know this much in detail for our AS chemistry syllabus. This is a bit of background knowledge into what I'm going to go. This reaction may scare you, but it is something that we've done in O levels, and it may be something that may be asked in A levels. They may give you half of this reaction and they may ask you to complete it. So, long story short, you need to know the reaction. This entire compound is a random fat. Okay, when this fat is reacted with 3 moles of NaOH, this is an ester, because we can see that there are 3 ester linkages, right? So this is an ester, it's a triester. Okay, so that is why we said it's a glyceryl triester, and so it is a fat. It reacts with NaOH, so this is basically alkaline hydrolysis. Alkaline hydrolysis had the same reagent. What happens? Let me clear this out a bit so you understand what I'm trying to do. What happens in alkaline hydrolysis? This bond will break, right? So when this bond breaks, all 3 of these will give you acids, and when all 3 of them give you the same acid, we will put a 3 over here, because 3 moles of the same acid, rather they go ahead and react with the NaOH and they form an acidic salt, right? So that is what we have done. But this part which is left over, let's look at that. This part. Now this is all connected. So H's will add across the 3 O's, as we can see over here. We can see that the H's have added across the 3 O's, and this is actually a triol because it has 3 OH groups, and this is called glycerol in simple terms. Its official name is 1, 2, 3 propane triol. You don't need to know this much detail, but you should be familiar with this entire reaction, because down to the simplistic basis, it is still alkaline hydrolysis. We are reacting a triester with alkali to form a salt born out of carboxylic acid and a triol. That is the only difference. So this is the commercial importance of alkaline hydrolysis. Now, a small note. You can see that the topic that I've written on top is esters extension. That means that this reaction is not in the syllabus, but it is something that you should still be aware of, that this possibility is existing in chemistry. Now over here, generally, to form esters, what is the condition? The condition is that we must have an alcohol and a carboxylic acid. But that condition is not always true. An acyl chloride and an alcohol may also chemically combine to form an ester. How? Let's look at that. Again, what will happen is that this will break and this will break. These will combine to form HCl and the rest will combine to form this ester. You can clearly see that we have a very stable ester over here. And so this reaction works. It is chemically acceptable and it is done in industries. So if you are out of carboxylic acids, you may use acyl chlorides. But this is not a reaction that is expected of you to know in the AS syllabus, because it is something that will be useful in the A2 syllabus. So generally, you should know that alcohols and acyl chlorides can react to form esters, and with that we finish the chapter. Thank you.